Okay, in this video I'm going to derive the PDF for an exponential distribution, this lambda times e to the minus lambda x. And in the text I said that actually we were not going to do this, but I decided that it really is too beautiful of an opportunity to pass up. It shows a lot of connections between the exponential distribution and the Poisson distribution and the binomial distribution and the geometric distribution. And what we're going to do is very similar to what we did for the Poisson distribution. We came up with a formula for the Poisson distribution by comparing it to a binomial distribution. Similarly here, we're going to come up with this PDF for the exponential distribution by comparing it to a geometric distribution. Okay, so to do so, we first need to get an exponential random variable. So let's let x be an exponential random variable with parameter lambda. Okay, and remember that lambda is the number of times we expect the event to occur in 1 unit of time. Okay. We cut up each unit of time into n subintervals of time. Where n is a large positive integer. And as we did with the Poisson distribution, we're going to eventually let n go to infinity and take the limit. But for now, we're just going to think of it as a large positive integer. I expect lambda occurrences of the event during any given unit of time. So if I divide that up into n subintervals of time, then the probability that the event occurs during any given subinterval, during a certain subinterval, is, well, expected to occur lambda times overall. I've divided that up into n subintervals, so it's going to be approximately lambda divided by n. Now it's not quite equal to lambda divided by n, and that's because I also should, in order to be exactly correct, I should consider the case where the event occurs twice during the subinterval. But so long as n is large, that probability that the event occurs 2 or more times during this small subinterval is extremely small, and it's negligible, so we're just going to ignore it. Now I'm going to let b be a positive integer, and we examine the probability that x is no larger than b. And we're going to get at this probability by comparing it to a probability for a geometric random variable. So we're going to let y be a geometric random variable with parameter what? Well, remember, a geometric random variable gives you how long you need to wait for an event to occur when the events can occur during discrete trials. And you have a trial and either the event occurs or it does not. And if it doesn't, you go on to the next trial. You go on to the next trial until you finally get to a trial where the event occurs. Well, our discrete steps, our discrete trials, are going to be these small subintervals. So the parameter p, the probability that the event occurs during one of those trials, is going to be the lambda over n that we discussed up here. Well, in that case, the probability that x is no larger than b, let's think about this here. That is the probability that the event occurs within the first b units of time. Each unit of time is being cut up into n little subintervals. So that's the same, approximately at least, as approximately the same as the probability that it takes b times n little subintervals for the event to occur. So it's the probability that the geometric random variable y is no longer larger than b times n. Okay, because n is how many little subintervals we have in a unit of time. So if we want the event to occur no later than b units of time, then we need it to occur no later than b times n trials, or b times n subintervals of time. Okay, now we can compute this probability exactly because y is a discrete random variable. It's a geometric random variable, and we've already studied those. You're used to dealing with them. Let's see here. So to get a probability for a discrete random variable, we just add up the probability of the individual numbers that are involved in the event. So this will be the sum from k equals the lowest possible value a geometric random variable can have is 1. So I'm going to start at 1, and then we go up to b times n. And I again need to change the font size here. B times n of, and then here I'm going to have the probability that y equals k. Okay, that's the probability that y is between 0 and b times n, which, since y could be no bigger than 1, this is the probability that y is between 1 and b times n, and since y can't be any smaller than 1, that's the probability that y is less than or equal to b times n. Okay, so we have this formula, and what I'm going to do is plug in the formula for the distribution of a geometric random variable. And that is 1 minus p. Now in this case, p is lambda over n, so I'll put it in a lambda over n. 1 minus lambda over n to the power of k minus 1 times lambda over n times p. Whoops, it wants to put that whole thing over a fraction. Let's highlight it and do that. Okay, so this is 1 minus p to the k minus 1 times p. That's the probability that the random variable y is equal to k, where p is lambda over n. And then I'm going to sum that up from k equals 1 to b times n. Okay, I'm going to do some algebraic manipulation on this guy. So the first thing I'm going to do here is bring that lambda divided by n out front. So we have lambda divided by n times, and then we have this sum. And I'm going to do something to the sum too. What I'm going to do to the sum is re-index it. Notice that I'm summing up 1 minus lambda over n to these consecutive powers, and k is ranging from 1 to b times n. So this k minus 1 is ranging from 0 to b times n minus 1. Well, what I'm going to do is re-index this so that my k goes from 0 to b times n minus 1, and then this power is just k. What I've done is I've taken that minus 1 and I've put it in these indices here. And what that will allow me to do is apply a commonly used formula for a finite geometric sum. And let me remind you of that formula. I bet you've seen it before, but it might have been a while. And that is that the sum from k equals 0 to, I'm going to say m instead of n, because I've already used n here. It shows up in a different context, of a number a to the power of k, that is equal to 1 minus a to the power of, it'd actually be 1 minus the next term in your sequence that you're adding up here. It's 1 bigger than that upper limit of summation divided by 1 minus a. And I just had those parentheses there, so it'd do the whole thing divided by 1 minus a. I'm going to take those off now. Okay, so that's a formula that you saw in calculus class, may or may not remember, and sometimes it actually shows up in algebra classes, if you have an algebra class that gets into geometric sums. Now in this case, I have the m is b times n minus 1, and I have the a is 1 minus lambda divided by n. So this probability that y is no larger than b times n, that is equal to, I'm going to take this, I got my lambda over n out front, I'll paste that down here. Okay, and then times, I'm going to paste this, my formula for a geometric sum, but a is going to be replaced by 1 minus lambda over n. Okay, so I'll replace it there, and then I need to replace it here too. Now the m is b times n minus 1, so if I add 1 to it, that's just b times n. So I'm going to replace that with b times n, and we're in business here. The first thing I want to know is that the denominator here, that's just lambda over n. I have 1 minus 1, that gives me 0, and then a negative and a negative come together and give me a positive. That's lambda over n on the denominator. That cancels with lambda over n over here. And we get that this is equal to just the numerator. So we have the 1 minus lambda over n to the power of b times n. Okay. Now I'm going to think of this as a double exponent. I'm going to think of it as, whoops, didn't want that there. I want the parenthesis here and here. If I have a power of b times n, then I could first raise it to the power n and then raise it to the power of b. And since when we have a power raised to a power we multiply, this will be the same thing as what was up here. Now why do I want to do that? I want to do that because notice right here, that's e to the minus lambda. Okay, that's how we've been defining e in this class. We did this for the Poisson distribution. If I have 1 minus lambda over n to the power of n, and I let n get really large, then that's very close to e to the minus lambda. So to get exactly e to the minus lambda, I'm just going to take the limit. And that's what we'll do here next. So we had that this probability is that, and we had that the probability that x less than or equal to b was approximately equal to that. So that gives us that the probability that x less than or equal to b is approximately equal to this expression here. Okay, and this approximation gets better and better as n gets larger and larger, and we can make it as good as we would like, simply by choosing n as large as we would like. What that means is that if I want to compute the probability that x is no larger than b exactly, then I take the limit. That's going to be equal to the limit as n approaches infinity of this. Let's put that in brackets here, or in parentheses. Okay, now I'm going to copy this expression here, so I want to use it again. Okay, that is equal to, let's paste that here. Now I'm going to pull the limit inside. Okay, the limit as n approaches infinity of 1 is just 1, so I'm going to leave that there. And that should just be a 1. And then I have the limit of this double exponent. Well, that b doesn't depend on n, so I'm going to put the limit inside here, pull it inside of that exponent, and whoops, it didn't put it where I wanted it to. Let's see if I can just move this. There we go. And this needs to go away. So we have that it's 1 minus this limit to the power of b, but we know that that limit is e to the minus lambda. So this is equal to 1 minus e to the power of minus lambda. Let's find my lambda here. To the power of b. Okay, because that limit again is e to the minus lambda. Well, then that just means that this probability is 1 minus e, I need to be in math mode, 1 minus e to the power of minus lambda b. Okay, now this is not our probability density function, and that's because we've already integrated our probability density function to get this probability. So if I think of this probability in terms of an integral, right, because x is a continuous random variable, then what do I get? I get that the probability that x is no larger than b is equal to the integral from negative infinity to b, and actually that b gets to stay there, that's convenient, of the PDF, f sub x of x dx. Okay, now so long as x is a exponential random variable, that's given how much time we have to wait for the event to occur, x cannot be negative. Okay, so I can redo this integral here. Let's see, and put it in text mode, put it down there, and start at 0 instead, because I know that my PDF is 0 for negative inputs. So that's the integral from 0 to b of my PDF. And I'm going to go ahead and stick this probability on the left-hand side. And here's where the fundamental theorem of calculus comes in. I'm going to take this expression and I'm going to do the derivative of both sides with respect to b. Okay, so I'll do that using this ddb. That means take the derivative of what's to the right, okay, with respect to b. And what do I get? Well, the fundamental theorem of calculus says that if the upper limit of integration is equal to my variable that I'm taking the derivative with respect to, then this is just the integrand evaluated at that variable. Okay, so this is just equal to, let's turn it into math mode, equal to, okay, f sub x of b. Okay, but we also have an expression for this. The probability that x is no larger than b, we just went through a bunch of work to find an expression for that. And that was, let's see what that was. That was this 1 minus e to the power negative lambda b. So let's put that in here. Okay, and we're going to take the derivative of it because this is the probability that x is no larger than b. We want to take the derivative with respect to b. Okay, so I have that the derivative of the probability that x is no larger than b is the derivative of this expression, and I can put this expression in parentheses like this. And that derivative is going to be equal to the PDF evaluated at b. So that means, okay, because they're both equal to the derivative of the probability that x is no larger than b with respect to b. That means that my probability density function f sub x of b is equal to the derivative of this with respect to b. Well, the derivative of constant is 0, and the derivative of e to a power is just e to that power, but then the chain rule says I need to multiply by the derivative of the power. And the derivative of minus lambda times b, when we're taking the derivative with respect to b, is just minus lambda. So I have negative minus lambda, that's positive lambda, times e to the power of minus lambda times b. Okay, and if I replace those b's with x's, then I end up with exactly the formula that we're going to be using for the exponential distribution. Okay, so there was a derivation for the formula for the exponential distribution. You will not be expected to reproduce this. This is a little more involved than I really think I'm going to require you to do in this course. Nevertheless, I thought I would produce this video to show you that it really doesn't just come out of nowhere, but that it builds off the basis of the geometric distribution, which we have already worked with and you've probably got the hang of by now.